We've seen these equations already in our work in one-dimensional kinematics. And what we're going to do here in this video is expand those to projectile motion, or motion in 2 dimensions. Now, the trick to expanding this is to realize that for a projectile, assuming there's no air resistance, the x acceleration is equal to 0. That is, the acceleration in the horizontal direction is going to equal 0. The acceleration in the vertical direction is going to be equal to g, typically, 9.81 meters per second squared, assuming we're on Earth. If I give you a problem on Mars or the moon or something, then that value will be something other than 9.81. But typically for what we're going to do, it's going to be 9.81 meters per second squared. Now, the deal is that these equations apply in the x direction, and they also apply in the y direction. However, since the acceleration in the x direction is equal to 0, what that means is that some of these equations pretty much disappear. You can look at this one in the lower left. If the acceleration is equal to 0, that just means that the change in the x velocity is 0, which means the final x velocity and the initial x velocity are equal to each other, which means in the x direction, the projectile isn't speeding up or slowing down. So this equation pretty much disappears. Same thing is true with the no time equation. If a is equal to 0, then this term disappears completely, and it just says that the velocity in the x direction squared at the end is equal to the velocity in the x direction squared at the beginning, which doesn't tell us really anything useful either. And in the x direction, if the acceleration is equal to 0, you can see that this term will go away, leaving us with only that portion that applies in the x direction. And isn't it true that that equation is essentially identical to that one right there? In the x direction, therefore, the only equation that really applies is this one in the lower right. All of the equations apply in the y direction. And that is why I came up with this chart to help us focus in doing the problems. You see here in the x direction, it's basically just d is equal to v times t. The displacement in the x direction for something that's launched in the air is equal to the velocity in the x direction multiplied by the time that it's in the air. All 4 of the equations, however, apply in the y direction. These equations here are identical to the ones that I showed earlier. I've just added some y subscripts to indicate that they occur in the y direction. And what we can do is we can use this little Venn diagram thing here to help us focus on what we have and what we're able to find. The common denominator between the x direction and the y direction is time. Now, the best way to do this is just to try a few problems. So here we go. We've got a rifle bullet, and it's fired horizontally with an initial speed of 850 meters per second from a height of 1.73 meters. So the height above the ground of this gun is 1.73 meters, and we want to find the time that the bullet is in the air. So clearly, we're looking for time. It says that the bullet is fired horizontally. Horizontally is in the x direction. So Vx is equal to 850 meters per second. The bullet will be in the air for as long as it takes to fall downward 1.73 meters. Therefore, the displacement in the y direction, leave a little space after this equal sign before you write 1.73 meters. We need to talk about that. What else do we know? We're assuming we're on Earth, since we aren't told that we aren't. So that means that the acceleration in the y direction, again, leave a little space after the equal sign, is going to be 9.81 meters per second squared. I asked you to leave a little space here after these equal signs because when we're dealing with projectiles, we need to be very careful about signs, particularly in the up and down direction. And it doesn't matter in which direction, up or down, we choose positive to be, but we have to be consistent with that. So I'm going to choose up to be positive. And if up is positive, then this bullet is falling down 1.73 meters. It must be negative. The acceleration is due to gravity. Gravity is pulling towards the Earth in the downward direction. That number must also be negative, which means if we look at our diagram here, what do we know? Well, we're looking for time. We know Vx. We know dy. We know ay. Is there anything else we know? And the answer is yes. There is one other thing we know. We know that the velocity initially in the y direction is 0 because it says that the bullet was launched horizontally. In other words, at the very instant of launch, the bullet isn't moving in the upward or the downward direction. And that means if we know those three things and we're looking for time, I think we can use this equation right here at the bottom. We know dy. Vy initial is 0, so essentially that's going to disappear. We know what ay is, and we can find time. So let's use that equation. dy is equal to Vy initial times time plus 1/2 ay time squared. Vy initial is 0. If we solve this for time, we're going to multiply both sides by 2, divide both sides by ay, and take the square root. You go ahead and take some time if you need to convince yourself that that's what this solves for if we're looking for time. So let's put the numbers in. 2, dy is negative 1.73. I'm going to leave the units off because we checked them. You can see here that the negative signs disappear. Make sure that you take the square root of this whole thing, not just the square root of the numerator. And when you do this, you get 0.59. I'm looking at significant figures now. 4 seconds. That's how long this bullet is in the air. You might look at what's given here, 850 meters per second, and think that we should round this to 2 significant figures, but we didn't use the 850 in this calculation. What we did use was the 1.73. Therefore, the answer should have 3 significant figures. Let's now find the bullet's range, which is the maximum horizontal displacement. Whenever we say range, we're talking about the displacement in the x direction. Now, what equation is going to be useful there? Well, clearly, that is this one. It's the only one that has dx. We're now looking for dx because we found the time that this bullet is in the air. So I think we're just going to take Vx times time. 850 meters per second times 0.594. I'll go ahead and write the units in this time just to prove to you that things are consistent. Those second units cancel. Now, if you type this in, you get an answer something like this. But that has too many significant figures. In fact, 505 has too many significant figures. That has 3 significant figures. And based on that 850 that's given, we need to round our answer to 2. So the best answer, if we're being picky, is going to have to be expressed in scientific notation. 5.0 times 10 to the second meters to two significant figures. Let's now find the bullet's height above the ground at 0.38 seconds. Now we know what the time is, 0.38 seconds. It's no longer 0.594 seconds. We also know what AY is. AY is negative 9.81 meters per second squared. We know what Vy initial is. It's 0. So let's look at our equations here and see if we can find what we need. We've got the time, we've got AY, we've got Vy initial, and we want to find the height above the ground. Now what we're going to calculate is initially not the height above the ground. What dy is the distance downward that it has fallen. So let's find that first. And the equation that we want to use could be any number of these up here, but why don't we use that one again? Here we go. dy equals Vy initial times time plus 1/2 AY times squared. Vy initial is 0, so this term disappears. The distance downward that this thing will have fallen in 0.38 seconds is 0.71 meters. Notice that it comes out negative because the bullet is falling down, and if you can see at the top left corner of the screen there, we chose upward to be positive, so it shouldn't surprise us that the bullet displaces in the negative direction. That is how far downward it's fallen. But the question here is, what's the bullet's height above the ground? It started at a height of 1.73 meters above the ground, and it's fallen downward 0.71 meters, which means at the time in question, the height above the ground for this bullet is 1.02 meters.